Just about everyone knows that a typical automobile gets its power from an engine under the hood. But how many people can say they actually know how that engine works? While a modern internal combustion engine is obviously an extremely complex piece of machinery, the basic principle behind it is pretty simple. Let's take a closer look. At a high level, a gasoline engine can be thought of somewhat like an air pump, except that the exhaust coming out is more of a side effect. This pump's real purpose is to rotate an internal shaft, which in turn rotates the vehicle's wheels. It does this by connecting that shaft, called a crankshaft, to pistons that move due to a mixture of air and gasoline combusting inside their cylinders, which creates a sort of chain reaction that keeps the engine turning. Before getting deeper into this process, let's first touch on the two main parts of an engine. On the bottom, a lower block is home to the pistons, cylinders, and crankshaft, the latter of which sends the engine's power out to the transmission and wheels. And above, the head contains the top of the cylinders and manages their airflow and combustion through valve train, fuel injection, and ignition systems. So let's explain that part a little more. You may have heard the term four-stroke to describe a vehicle engine. This refers to its 4 stages of operation. First, the piston moves down, creating a vacuum in the cylinder chamber that pulls air in through precisely controlled intake valves. Next, the valves close and the piston raises back up, compressing all that air, along with some gasoline that was mixed in from the fuel injection system. Now the fun part. The ignition system creates a spark at the end of the spark plug, creating a controlled explosion of compressed air and fuel that sends the piston back down. Then finally, the piston moves back up, pushing that spent air-fuel mixture through the exhaust valves and out to the, you guessed it, exhaust pipes. And since we're dealing with multiple cylinders with pistons all working from the same crankshaft, each one essentially creates the 4-stroke process for the next one. Pretty ingenious, right? Now, speaking of multiple cylinders, let's talk about the various engine configurations. 4-cylinder engines are probably the most common design these days, but who doesn't love a V6 or even a V8? These terms simply refer to the number of cylinders in the engine and their layout. Nearly all 4-cylinder engines have their cylinders arranged in a row, called inline or straight. But it's also pretty typical to see engines group their cylinders into 2 banks connected at an angle, a V. Doing it this way effectively cuts the engine length in half, enabling it to fit more easily under the hood. So a V6, 3 cylinders on either side, creating a V shape. And what if that V shape was opened up all the way, a 180-degree angle? Well, then you'd have what's called a boxer or flat engine design. Alright, so what about those other numbers you always see? 2.0, 3.5? Well, that refers to the engine's displacement, often simply thought of as its size. That number is literally the volume, in liters, that the pistons displace with every engine cycle. So essentially, if you were to fill up the cylinders of a 2-liter engine with liquid, it would take, well, 2 liters. And if it's a 4-cylinder engine, each one displaces half a liter. So what's the end result of all this? Power. The measurable output of an engine is called its torque, basically the strength with which it turns its crankshaft. Torque is measured in pound-feet, which, as the name implies, is the force created by 1 pound of weight at a distance of 1 foot. Imagine a 1-pound weight sitting at the end of a 1-foot wrench. That nut is being turned with 1 pound-foot of torque. So now, going back to the displacement concept, bigger cylinders pull in more air and fuel, typically resulting in more muscle. They turn the crankshaft with more force, which is perfect for large vehicles, towing, or even just spirited driving. So now you're probably thinking, isn't that horsepower? Well, yes and no. In fact, horsepower doesn't technically exist. Okay, yes, that requires a bit of explanation. Horsepower is obviously a real thing, but it's actually a calculation, not a physical measurement like torque is. It's basically torque over time. So this means the faster that engine turns, its revolutions per minute or RPM, the more work it can do and the more horsepower it has. Put in extremely simplified terms, torque times RPM equals horsepower. But that doesn't mean making big horsepower is as simple as spinning the engine faster, since that takes more and more energy as the engine speed increases. And as that torque decreases, the horsepower calculation eventually can't keep up either. This is also why transmissions are so critical in keeping everything in the appropriate sweet spot. But that's a topic for another video. So that's the general idea behind internal combustion engines. But this was just a high-level look at the basics, Engines 101 if you will. There's obviously a whole lot more to say about engine tech, so be sure to check out the other videos in this series to learn more. You've probably heard the term turbocharger before, and maybe supercharger as well. You probably also know these have something to do with adding power to a vehicle's engine. But do you know what they actually are and how they work? Let's find out. In the first Engines 101 video, you learned the basics behind internal combustion engines. They suck air into a cylinder, mix it with fuel, and then burn it to move a piston, and then repeat. We then explained the idea of displacement and how larger cylinders usually mean a more powerful engine. That's because they're able to fit more air and fuel, essentially creating a bigger explosion. But there's also another way to achieve this, and it's called forced induction. You see, the engine design we described is considered naturally aspirated, which means it's simply breathing in naturally from the air around it. But the concept of forced induction changes this through components like turbochargers or superchargers. As the name implies, the idea is to force additional air into the cylinders, more than could just be pulled naturally from the engine's intake. By doing this, forced induction can effectively simulate large cylinders without actually having them, enabling a smaller displacement engine to put out the same power you'd typically see from a larger displacement unit. The cool thing here is that it allows for control over how and when it works, meaning that when extra power isn't needed, that engine simply acts like the smaller engine it is, saving fuel in the process. And again, that's because when there's more air, you need more fuel to match. And that's true whether through a turbocharger or larger cylinders. So how does it actually work? Let's focus first on turbochargers. A turbocharger, or simply turbo, can essentially be thought of as a highly engineered fan, compressing and blowing air into the engine as it spins. But what's great about it is that it does this without requiring any power for itself. That's because it's mounted onto the exhaust line, right after the cylinders, so the engine's own exhaust output is what spins it, which in turn pushes more air back into the engine and on, creating a remarkably clever self-powered loop. That said, because of this design, some turbos can suffer from something called lag, which essentially means it can take a moment before the exhaust can get it spinning fast enough for the added power to kick in. Similarly, superchargers also work by forcing extra air into the engine as they operate, but their design isn't quite the same. Instead of being driven by the exhaust like a turbocharger, they're connected by a belt directly to the engine, so when the engine spins, so does the supercharger. On one hand, this means no lag, which is great, but on the other, it means it's taking some energy away from the engine to operate, so the supercharger needs to make up for this deficit first before actually producing any extra power. This means it's not quite as efficient as a turbo, where all the extra power is free in a manner of speaking. Now, just like with engines themselves, both turbochargers and superchargers come in a wide range of designs and configurations. And this video is really just focusing on the general idea behind them. But as an example, the somewhat common twin-turbo design uses two turbos on the same engine. In some cases, they might be identical and simply work side by side to double up on the extra power, generally used in the case of V engines, where there's a turbo for either side. And in other cases, they might be a sequential design, meaning they work one after the other depending on when they're designed to deliver their power. For instance, a smaller turbo with minimal lag for everyday lower RPM use, and a bigger one to max out the power at higher RPM when it's really needed. And there's even some single turbo designs, often called twin scroll, that can vary their output in a similar way, providing the responsiveness of a small turbo and the big power of a larger one, all in one unit. This two-in-one design works by making smart use of the exhaust that spins it, pulling from alternating cylinders in order to create a smoother pulse flow that helps eliminate lag. So that's a quick look at the concept behind forced induction, turbochargers, and superchargers. These fascinating components really take engine design to another level, an engineering magic trick that allows smaller engines to pretend they're larger engines. But as mentioned, this video is just scratching the surface on automotive engines, so be sure to check out the other videos in this series to learn more. In this installment of Toyota's Engines 101 series, we're taking a closer look at one of the most critical parts of an engine, its valve train. This component has a massive impact on the overall performance and character of an engine since, in a nutshell, it's how the engine breathes. So let's first explain what exactly constitutes a valve train before getting into some more advanced aspects like how valve timing works and how it can be used to enhance not just performance, but also efficiency. Without a valve system, the entire concept of an internal combustion engine simply wouldn't work. An engine's cylinders need intake valves that open to pull air in and exhaust valves that open to push the exhaust gases out, effectively inhaling and exhaling with each cycle, creating the power that ultimately turns the wheels. These valves are opened and closed by a component called a camshaft. By aligning the camshaft's lopsided lobes with the valves, it can push against them as the camshaft turns, opening each one with every rotation. And since this camshaft is connected to the crankshaft, the valves stay in time with the rest of the engine, regardless of RPM. Valve train design can vary in a few common ways: how many valves there are, how many camshafts operate them, and where the components are located. First, most engines nowadays use 2 valves on the intake side and 2 valves for the exhaust, making for 4 per cylinder. Next, some vehicles use a single camshaft to manage both intake and exhaust valves, while others use a dual camshaft layout with 1 for each side. Finally, while most modern vehicles have the camshafts mounted above the valves to simply control them directly, some also place the camshaft below the valves, in the block, and instead use a system of push rods and rocker arms to actuate the overhead valves. So, have you ever seen a vehicle with a 16-valve or DOHC badge and wondered what that meant? Well, 16-valve on a 4-cylinder engine indicates that each cylinder has 4 valves. And DOHC stands for Dual Overhead Cam, which further describes that vehicle's valve train layout: 2 camshafts positioned above the valves. So that's how a valve train works, but it's not the whole story. Timing those valves correctly is a delicate tightrope walk between smoothness, efficiency, and power. We're talking fractions of a millisecond making a huge difference. That's why hitting an ideal balance at 1500 RPM might require a different timing than at 5500 RPM. That's where variable valve timing comes in. Nearly all auto manufacturers have a variation of this technology, and Toyota's is known as VVTi, or Variable Valve Timing with Intelligence. The details of this feature can vary by model, but the goal is the same. The basic design centers around the cam gear that pairs the camshaft to the crankshaft. By implementing an internal shifting mechanism within this gear, the rotation of the camshaft can be pushed slightly forward or backward, which then advances or delays the opening of the valves accordingly. This way, valve timing can be adjusted without impacting the rest of the engine cycle, which in turn enables the ability to maintain an ideal balance across multiple RPM ranges. Now, this brings us to our next point. Instead of targeting a perfect balance, what if valve timing could be adjusted to maximize efficiency? Well, this is exactly the thinking behind Toyota's modern take on the Atkinson cycle engine design. This design takes a different approach to combustion compared with the usual Otto cycle engine of a typical vehicle. Without taking a deep dive into automotive history, the general idea is this. With the Atkinson design, the intake valves are kept open into the compression stroke. This effectively shortens that stroke while still maintaining an expansion ratio based on the full cylinder. This in turn results in a lower compression ratio, reducing the energy needed to compress the air-fuel mixture. The benefit here is that virtually all of the fuel is burned while still inside the combustion chamber, helping to reduce emissions and maximize efficiency. The flip side, however, is it means that the pistons aren't firing with the maximum possible amount of pressure and power. This trade-off in power is why Toyota is selective about when it gets used. For instance, it makes sense to use it when full power isn't needed, like highway cruising. This is the idea behind Toyota's wide-range VVT-iW system, where the engine can flip between auto and Atkinson modes as needed. It also makes sense to use Atkinson cycle full-time if it's being supported by an additional power source, like an electric motor. This is the thinking behind a typical Toyota hybrid powertrain. So that's a brief look at the valve train design of an internal combustion engine, not just what it is and how it works, but also how its timing can be adjusted for either an optimum balance of power and efficiency, or even to crank the efficiency to the max. To learn more about the technology inside Toyota vehicles, or even just automotive engineering in general, be sure to check out the other videos in this series. If you've ever been to a gas station, you're probably aware there are two main types of automobile fuel: gasoline and diesel. And while they both come from the same source, petroleum or crude oil, you're probably also aware they're not interchangeable. Filling up with the wrong one can do serious damage to your engine. But why is that? What's the difference between a gasoline and diesel engine? Let's find out. In the first Engines 101 video, we broke down the 4 steps, or strokes, of a gasoline engine cycle for a typical vehicle. Well, a diesel engine follows a nearly identical process. Let's first recap how it works on a gasoline engine. First, the piston moves down, creating a vacuum in the cylinder chamber that pulls air in through precisely controlled intake valves. Next, the valves close and the piston raises back up, compressing all that air, along with some gasoline that was mixed in from the fuel injection system. Now the fun part. The ignition system creates a spark at the end of the spark plug, creating a controlled explosion of compressed air and fuel that sends the piston back down. Then finally, the piston moves back up, pushing that spent air-fuel mixture through the exhaust valves and out to the, you guessed it, exhaust pipes. And since we're dealing with multiple cylinders with pistons all working from the same crankshaft, each one creates the 4-stroke process for the next one. So diesel and gasoline engines both share this same general process, but that third step, the combustion stroke, is where the key difference lies. While gasoline engines typically introduce their fuel during the first intake stroke, and then rely on a spark plug ignition system to set off combustion, diesel engines simply ignite from the pressure alone. If you remember your science classes, you might recall that things get hotter when they're compressed. And that's exactly what happens in a diesel engine. Their compression ratios are much higher than in a typical gasoline engine. So when the fuel is introduced into the cylinder, the air is already compressed and at its hottest point, so that's all it takes to ignite it. No spark needed. This high compression system offers 2 big benefits: great fuel efficiency and tons of torque. That extra muscle is exactly why diesel is so often found in heavy-duty applications like long-haul trucks, utility vehicles, and heavy-duty towing. So with all that engine strength, why aren't they also popular for high-performance sports cars? Part of it comes down to their design, limiting their RPM range and, as a result, their horsepower potential. But the bigger reason these engines aren't really found in sports cars is simply that they're heavy. And vehicle weight is the last thing you want when it comes to maximizing speed and agility. This added weight is due to the high compression design mentioned earlier. These diesel engines need to be built strong enough to withstand that higher internal pressure. Now, another interesting difference is how the power output is controlled. On a gasoline engine, the accelerator pedal controls the throttle valve, an opening which dictates how much air can be pulled into the cylinders. Whereas on a typical diesel, that throttle body doesn't exist. It's just always wide open. Instead, the accelerator pedal directly controls how much fuel gets injected. This works because diesel engines can operate on a much wider range of air-fuel ratios than gasoline engines. Beyond that, there isn't much difference between the two. Just like gasoline engines, diesels can also benefit from forced induction systems like turbochargers. In fact, turbos are so common in diesels, you'd be hard-pressed to find a vehicle without one. So that's a brief look at how a diesel engine works and how it differs from a gasoline engine. But this is just one topic in a wide world of automotive technologies, so be sure to watch the other videos in this series to learn more about them.